So how is everyone today? Good, I hope? All right. So to recap and to finish up what we were talking about last time, last time we began a discussion of the predator-prey model, the Lotka-Volterra system of differential equations, and we were considering a specific case where dr dt is 0.08 r subtract 0.001 r w, and dw dt is negative 0.02 w plus 0.404 2 RW. All right. So the meaning of the letters, okay, the symbols, is that R is chosen for rabbit, honestly, and W for wolf. So what it is there's two creatures. Okay, there's two creatures, and the wolves eat the rabbits. All right, and then T is time. So not two creatures, but rather two kinds of creatures. Okay, so then let's remember that. Let's try and remember what each one of these means. So dr dt, what that represents is how is the rate of change in the quantity of rabbits. So, like, if the conditions are good for the rabbits, what would you expect about dr dt? It should be positive. And if they're really, really good, then it should be, really positive, like big, If the conditions are real bad for the rabbits, then what should be true about dr dt? Yeah, it should be negative. Dr dt should be negative. Which would indicate that, so if dr dt is positive, that means that the rabbit population is increasing. If it's negative, decreasing. If dr dt is 0, what's true about the rabbit population? It's constant, right? It's not changing. Okay, similar things about the wolves, okay, about the SIGN of dw dt. Now, let's look at each one of these individual terms. So looking at that term by itself, dr dt is 0.08 r. More or less what you can interpret that to mean is that for a given population of rabbits, that's about how fast the rabbits increase themselves through reproduction. Okay, so then the amount of new rabbits is proportional to the amount of current rabbits. Okay, just like all other creatures. Okay, so then what's the interpretation of that? Yeah. So because this is negative, R and W, those are quantities of rabbits and wolves respectively, so R and W are positive. Okay. So this term right here that we're looking at is negative because it's being subtracted. So this is saying how fast the rabbits are going away. So this number right here, the 0.001, that's something that in principle you'd go out and measure, like in a population. You'd have to go perform some measurements. It's not at all clear why the number should be this. Okay, this is you go perform a study in a part of the woods and you track the rabbit population. Okay, but why should the rate at which rabbits die be proportional to the number of rabbits? Because the fact that it's this constant, which is found, in a real experiment by measurement, why should the number of rabbits that die be proportional to the number of rabbits? Right. Well, okay. So let's say this. Here's a tragic fact. It's something like 17,000 children under the age of 5 die every day. That sounds atrocious, doesn't it? and it is. But on the one hand, it's a little bit less atrocious when you come to the realization that there's 7.5 billion of us. Okay, so 17,000, that's a lot of children under 5 that die every day. But it's not so much compared to how many human beings there are altogether. So why should the number of rabbits dying be proportional to the number of rabbits? Well, because the more rabbits there are, the more likely, the higher numbers of rabbits per day are going to die, if you like to think of it that way. And then why should it also be proportional to the number of wolves? Yeah, because that represents the likelihood, more or less, the likelihood of a rabbit meeting a wolf and winding up in the wolf's stomach. Right? So then let's look at these other ones. So this is you can imagine this basically to be a measured quantity of how fast wolves die. They just this is how fast they die. That's something that you would go out in the field and measure. And that's another field measurement that you'd make. So the number of new wolves is also proportional to the number of rabbits and wolves. So the number of new wolves coming to existence has to be proportional to the number of wolves, because you can't make baby wolves without adult wolves. And furthermore, you can't carry a wolf pregnancy to term without sufficiently many rabbits. So yes.
So if you had a third animal that relied on the wolf population, you would have 3 rabbits?
Yeah, yeah. So I mean, you can make it as neat as you want it. These ones eat those ones, and those ones, but not these ones. Yeah, all kinds of crazy business. Okay, so then this system is this kind of system is called a predator-prey model. So we established that you can use the chain rule and the implicit function theorem to figure out the derivative of W with respect to R, which is to say how fast do the number of wolves change as a function of the number of rabbits. And doing that, you obtain the following: negative 0.02 W plus 0.402 RW. And then this one, 0.08 R, subtract 0.001 RW. All right. So then that's neat. So again, from last time, that's a consequence of the chain rule and the inverse function theorem. Now notice that this right here, this statement doesn't depend on t. Doesn't depend on t, whereas these other ones do. So if we were to plot this now, so D, this would be the W axis, and this the R axis. Now we found there's just one non-trivial stationary point where both of them are 0. That is, we found that when the number of rabbits is 1,000 and the number of wolves is 80, that particular place is where the populations are stable. So that doesn't mean that no rabbits die and that no rabbits are born, and it doesn't mean no wolves die and no wolves are born. Rather, it just means that the number of rabbits being born and dying offset each other exactly. Okay, so if it ever came to pass that there were exactly 1,000 rabbits and 80 wolves, then the population would just be exactly there and stable. So now let's plot a little bit of a slope field so that we can see. What if we're right here, say, at maybe that's like 1,100 rabbits. So that would be 1,100 rabbits and 80 wolves. And the question is that what would be the slope there? So how do we figure that out? We plug it in. In fact, that's not even going to work, is it? 1,100. Yeah. So let's plug that into here. Evaluate dW dr evaluated at that point. So that would be negative 0.02, and then W would be 80 plus 0.00002 RW, and then over 0.08. Whoops, I didn't want to write RW. I wanted to plug in the values. R and then RW. So R is 1100. 80. All right. So type that into the calculator there. $80 plus 0.00002, 1100. All right. So I did it carefully. Oh, okay, of course, I got to divide by 0. So what does that mean? Who can interpret that for us? Did I type in, did anyone do it on their calculator? Or did you get a divide by 0? Or did you get a number?
I got a number.
Sorry?
I got a number.
You did? Okay, then I did something wrong here. 1100. .0H, 1100, blah, blah, blah. Okay, well, I keep getting a division by 0. I kind of expect to get one. So what number did you get then?
Oh, maybe I did the wrong thing.
So what does that mean? You know, we're trying to calculate a slope. Trying to calculate a slope. So what does that mean when, if I'm calculating a slope and I'm getting a division by 0? Yeah, it's vertical. Okay, so that makes sense. So right here it would end up being vertical, the slope. Okay, so now you can imagine slowly and laboriously and tediously plotting a bunch of points and you know, calculating the slope at all those points. Right? You can imagine doing it. And if you were to do it, it would end up looking like this. Something like that. And you could plot some more. You know, this is you know, kind of the reason why, in my opinion anyway, humans organize themselves into societies to make computers, so you wouldn't have to do all this calculation by hand. So you can you know, calculate these slopes at a variety of places all over the place. Okay, I'll do one more loop. So what if you were back in the day with Lotka and Volterra, you'd be plotting these by hand. So what this is saying, the way to interpret this is that if it ever came to pass that you were right here, that you found yourself and you arranged matters so that the forest had exactly 1,000 rabbits and 80 wolves in it, then over time the populations of these two species would not alter. They'd just be constant. But if you were to get, say, right here, So what this is saying, we're to the right of the equilibrium point, meaning that we have a surplus of rabbits, right? Because what this stationary point is saying, it's saying that in order to support exactly 80 wolves, you need 1,000 rabbits. But if we're over here, that means we have more rabbits. So if there's more rabbits, then that means we can support more wolves. So what will happen to the number of wolves as time increases? Yeah, it'll increase. But we have to follow this slope. So what's going to happen is we follow this around just a little bit. So what that's saying is that, oh, the number of wolves is increasing because now we're up here. And the number of rabbits is decreasing because those rabbits are being turned into wolves, right? That's what's happening. And so then now, more or less, we get to right here at that point. Now we're back at 1,000 rabbits, and we've got a surplus of wolves. So we're like maybe at say 1,000 rabbits and 90 wolves. So now that's too many wolves. That's too many mouths to feed. Okay, so the wolves are going to continue eating the rabbits, but because there's less and less opportunity to find a rabbit because there's not enough rabbits and too many wolves, what's going to happen to the number of wolves? It's going to decrease. Okay, and then it just goes around and around. The circle of life, right? Ha ha ha. So, if you what this model is saying is that wherever you are on this slope field, the slope field is telling you at every time where the joint populations are going to move, and they're going to end up following these arcs. So, as a result of this consideration, you can plot the number of, versus time, the number of rabbits, and versus time, the number of wolves. So according to this, I started it right there where we had a surplus of rabbits. So the equilibrium point of rabbits is 1,000. Okay, and we started with slightly more rabbits than the system would be stable at. So as a result, the number of rabbits is going to decrease. Okay, so it's the number of rabbits decreases to some minimum value, and then it starts swinging back around. Because now that all those wolves have died, okay, now there's lots of room for more rabbits. So the number of rabbits increases. And it's just going to do this cyclically. Now this is not really a sine curve. It's not exactly a sine curve. The reason why it's not a sine curve is because that's not exactly a circle. It's more like and it's not an ellipse either. It's just a sort of spread out circle. Similarly, the number of wolves, the equilibrium number of wolves is 80. And we started out with exactly 80 in the hypothetical thing that I said. And because there was a surplus of rabbits, that means that we were able to turn some of those rabbits into wolves. So the number of wolves increased. And then it decreased. And then it increased. Right? Like this. Good. So now, that's the Lotka-Volterra model. And it's neat. It's a neat thing. It sort of shows you some neat stuff, but it does have some fairly severe limitations. One of its limitations is that well, if it ever comes to pass, for example, that there's no wolves, that the number of wolves is 0, then it's saying that one true thing it's saying is there's not going to be a spontaneously generated wolf, right? So that means that that whole equation goes away, and that whole term goes away, and then suddenly that's what you're left with, if ever it comes to pass that there's no wolves. So now that's an exponential model for the number of rabbits, and that's not realistic. So why is that not realistic? Yeah, because actual populations are constrained by the carrying capacity of the environment. Okay, so you can't have an exponential model for the number of rabbits in a forest. A more interesting variation on this model that we won't really talk about is when you start adding in and saying that, well, the number of rabbits is not going to be exponential, and the number of wolves won't be either. Rather, we're going to make it logistic. So when you add in sufficiently many factors in terms to make it logistic, instead of having closed loops, trajectories which are loops, what will happen is that the trajectories become spirals, either spiraling in or spiraling out, or you can have closed loops that are attractive and things like that. So in real life, when you have environmental pressures, these arcs usually aren't closed loops. Yes?
So if we were to introduce a third factor to this, when drawing like the graph, that'd be three-dimensional?
Yes, and in that case, see what I'm doing here is I'm drawing little one-dimensional slopes. You'd have to draw it in 3 dimensions, and at every point, instead of drawing little one-dimensional bits, you draw little 2-dimensional bits, little pieces of plane, and they'd be pointy, and you'd say, we're going to go that way. But yeah, you can. This just generalizes to any number of creatures.
How would you graph the force?
Well, you would just there's I mean, obviously no way to do it, right? Like as a picture, but you could do it as a movie, or you could say, I'm going to select just these 3, and here's a picture with just these 3. Here's another picture with just those 3. Here's another picture with just those 3. But there's no way to to draw a 47-dimensional object and for us to make sense of it as a picture. Good. Now, so to give you an example, because the book just mentions it just briefly. So can you see it? So this phase plot, this plot right here, is what the model looks like when you add logistic terms. Okay, so then you can see that instead of being a closed loop, you actually end up spiraling on to the stability point. Now this is important because, surprise, surprise, one of the most important things that human beings found out as a result of the invention of the telescope and microscope is that besides wolves eating rabbits, we've got bacteria eating us. Huh? Yeah, so then, so here's the deal. Is that that we fit in that predator-prey model, and we're not the predators. We're the prey, right? So you might ask, how can you drive a predator? How can you drive a predator to extinction, right? Because we don't want anything preying on us. Okay, and this has to do with vaccines and epidemiology and things like that. So we've successfully driven, for example, smallpox to extinction. It's not completely distinct because some governments have weaponized versions of it, but it's not in the wild, so that's good. But the reason why you can do that is more or less because there's a system of differential equations that was solved and figured out by biologists, and they figured out, oh, this is what would be necessary to cause the stability point to be 0. And it was driven to 0 by concerted action by the United States and the Soviet Union. Also, smallpox is a pretty easy one because there's only 2 outcomes of getting smallpox. Okay, there's only 2 possible outcomes, and they both mean that you can't get smallpox again, because one of the outcomes is you die, and that's about 50%. So if you die, you can't get smallpox again. And the second possibility is that if you get smallpox and you don't die, then you have immunity for the rest of your life. So that makes smallpox very easy to attack and drive to 0, unlike the flu, right? You can get the flu as many times as you want. So, or don't want. So because of that, and these differential equations, we're able to destroy the predators attacking us. Very good. So now we're in section 10.1. So parametric equations. Parametric curves. All right. So to sort of raise the discussion, you know, I can just draw silly little plots here. And then ask concerning each one of these. So, you know, if I write x and y, so that x and y are in their usual locations, I could ask, what's plotted? Is it a function of x? It is, right? Because it passes what? Vertical line test. Okay. How about this one? Is this one a function of x? No, it's not a function of x because it doesn't pass the vertical line test. But, you know, you could in some sense say, well, I can still kind of deal with it like a function because if I turn it on its side, then now, even though it's not a function of x, it is a function of what? Y. So I can, you know, we can still kind of use our same tools. But how about this one? Is this one a function of x? No. Is this one a function of y? No. So, like, we can't do the same trick of just like saying, okay, well, this way or that way. So, no matter how you twist it, it's not going to be a function of x or y. Nevertheless, you know, we want to be able to, you can imagine, like, make a machine that actually plots this. You know, to like draw it. You know, have you ever seen one of those machines that has a, you know, it's got a rail, and on either side it goes, and then it's got one of these that goes side to side. Your printer is one of those things, right? If you've got an inkjet printer, and it goes, you know what I'm talking about? So imagine such a machine that had a pencil, a literal pencil, that, you know, traces it out like that. So, like, you know, my hand is one such machine. But you can imagine a mechanical, like a electromechanical machine that does that. An example would be like, you know, when you go to the, if you want to get like a custom sticker made, that's not like you're not going to make millions of copies of this sticker, but you want just some custom thing. They make, you know, sticker sheets where you can plug a program into a computer, and then it has a knife, and it just cuts it out of the sheet for you. A little knife. And so the question that we're considering is how do you describe how that knife should move? Or if you wanted it to draw with a felt marker, you know, and draw something neat, how can you describe how that thing is supposed to move? So, you know, if you wanted to write words, most of the letters, many of the letters in our alphabet aren't functions of x or y, you know, in the usual orientation. But nevertheless, we need to be able to draw them. All right. So the way that we do this is with these things called parametric equations. So probably best to start with an example. So suppose that we say, okay, I'm going to say that x is some function of t, and it's going to be t squared minus 2t. Okay, and moreover, y is going to be t plus 1. Okay, so we've got an x and we've got a y, but we also have this third variable t. So what I'm going to do is I'm going to make a table of values for t, x, and y. Okay, and we're going to evaluate at several values of t. So for -2, -1, 0, 1, 2, 3, and 4. And we're going to plug all these in and then plot them. All right? So when t is -2, we want to plug that in there. What do we get for x? So that'd be, well, squaring that, that'd be 4, and then subtract -4. So that'd be 8. And then this would be 1, subtract -2, so that'd be 3. And then 0. 1 minus 2, that'd be what, -1? 2, what am I trying to say? Did I make an error somewhere? Yeah, 4 minus 4, so that should be 0. And then 9 minus 6 would be 3. Oh, and I bet I know the next one. 8, right? 8. You know, because this is the same forward and backwards. A palindrome, you know, like race car. The word spelled the same forward and backwards, and so is taco cat. But that's not a word, you know. So if we plug in, if we do the same thing with y, this would be what? Negative 1, 0, 1, 2, 3, 4, 5. All right. So now, what I'm going to do is I'm going to plot those points. And I'm only going to plot the x and y values, but I'm going to write the t value at where I do it. So I've got a point 8, negative 1. All right. So then to make sure the scale is good, that says you know, there's a tick mark there, and there. But I'm going to take those to be 2. So that's 2, 4, 6, 8, 10, so that I can get all of that on the plot there. So 8, negative 1. So 2, 4, 6, 8, negative 1. So there's that's t is negative 2 there. And then 3, 0. So 3, 0 right there. 0, 1. So 0, 1. Negative 1, 2. There. 0, 3. 3, 4. And 8, 5. Interesting. Okay, so then now, it's not clear. You know, if I just sprang this on you, you wouldn't be able to tell me what order did I draw those points in, right? So I'm going to remind myself of this by just plotting. Well, there, that was when t was negative 2. This was when t was negative 1. This one when t was 0. T is 1. T is 2. T is 3. T is 4. Now, if we were to instead of plotting just those points, but if we were to plot lots and lots and lots of points, then, you know, or if you like, just connect the dots, it would look like this. And of course, that, you know, might remind you of that sketch right there. So now, what I want you to take away from this is that this is what this is telling you. This is telling you, in a sense, how to draw this, how to draw it. So in particular, we started there at that point, and then we proceeded moving that away. So we're moving like this. So, you know, one way to imagine this is sort of like a, you know, like a comet, you know, going through its through an orbit. It's going to take it, you know, first in to the solar system and then back out. Whew. Any question about this idea? So now this, I hope that you're getting a strong, what am I looking for? Echo of what we did with the Lotka-Volterra differential equations, because you know, have a look. These x and y, they both depend on t. But then we plotted something on an xy plane that doesn't have t on it, right? So this plot doesn't include t. And so it gives this trajectory right here, and we marked all the various times. So we're like following something. Good. So let's try another one. Where's the other pages? All right. But in fact, before doing this example, I'd like to remind you that here's something that you know, is that the cosine of theta squared plus the sine of theta squared is 1, right? That's the Pythagorean identity. So with that in view, let's consider, how about we write that x is twice the cosine of t, y is the sine of t, and we're going to do this for 0 less or equal t less or equal 3/4. 3 pi over 2. All right. So let's make a table, and let's draw a plot. So we need to go from 0 to 3 pi over 2 for the t values. So 0 would be a good place to start. What would be another t value that might be reasonable? 1? Well, we're going to be plugging those into sine and cosine. So, let's do some, stuff like pi over 4 maybe. So I'm going to do, just to make my life easy as possible, remember that for pi over 4, they're both square root of 2 over 2, right? And then for pi over 6, one of them is doesn't have a square root. And for pi over 3, the other one doesn't have a square root, right? Because cosine of what? Cosine of pi over 3 is half. And then sine of pi over 6 is half, or something like that. All right. So I'm going to do those. I'm going to do pi over 6, pi over 3, and then maybe pi over 2. All right, and then so that's straight up. So now we need to continue. So this would be what? 2 pi over 3. And then 5 pi over 6. And then pi. So that's in my mind, I'm tracing around the circle. So now we need to go down to 3 pi over 2. So so that would be 6 pi over 6. So 7 pi over 6 is the next one. And then what do we need to get to the next one? So that's 3 pi over 3, 4 pi over 3, and then 3 pi over 2. All right. So let's evaluate these at all these positions. All right. So cosine of 0 is 1. Multiplied by 2 is 2. Cosine of cosine of pi over 6 is half. And then multiplied by 2 is 1. Wait, is that right? No. Cosine of pi over 6. Yeah, square root, so square root of 3 over 2, and then multiply by 2, so this one is the square root of 3. Okay, which is about, as a decimal, is about what? It's about 1.7, right? So that's a good thing to know. So cosine of pi over 3 is half. Multiply by 2 is 1. Cosine of pi over 2 is 0. Multiply by 2 is 0. Cosine of 2 pi over 3 is negative half. Multiply by 2 is negative 1. And now you can, I hope you can see the pattern. What am I going to get next? Negative square root 3. And what am I going to get next? Negative 2. Okay, this one. Negative square root 3. No, is that right? Yeah, that's right. And then now this one? Negative 1. And this one? 0. Okay? Because we're cycling through the circle, right? So you have to have these, you know, right here, cosine is maximal. And we decreased to its minimum. And now we have to read those same things, but in the opposite order. All right? Now let's do sine. So what's the sine of 0? 0. The sine of pi over 6? Half. Sine of pi over 3? Square root of 3 over 2. And the sine of pi over 2? 1. Okay, so now, okay, we went from 0 to the maximum of sine. So now what are we going to do? Yeah, we're going to do exactly the same. So now we're going to have to read those things backwards, right? So now it'll be square root of 3 over 2, and then half, and then 0. So is that really correct? Is the sine of pi really 0? Yes. So now we're going to reach the negative part of sine. So now what? Negative half. Negative square root of 3 over 2. And then what? Negative 1. Okay, look, these are the same. They're symmetric across 0, except the one on the top is positive and the one on the bottom is negative. Okay, this is trigonometry. Y'all got to have this. Also, square root of 3 is about 1.7-ish. So square root of 3 over 2 is about 0.85. A little bit less than 1, right? Okay, so let's plot this. Oops. Oh man. What just happened? My tape lost its mind. Man, technical difficulties. Oh, and somehow I did exactly the same thing to this one. It's just not my tape day. All right. I'll just tape it later. So plotting these. At time 0, we're going to plot the point 2, 0. So now, because these go between 0 and 2, and because these go between 0 and 1, I'm going to take these to be halves. Okay, so that's half, 1, 1 1/2, 2. So 2, 0 will be there. Okay, then square root of 3 over 2, comma, half. So I'm going to be at this height, and then square root of 3 is about 1.7. So that's 1 1/2. That's 1.75, so that's about 1.7, so something like that. Okay, now x is 1, so that'll be there. And then y is square root of 3 over 2, that's 0.85, so that's going to be about there. Then 0, 1, so that'd be right there. Okay, and then the rest of the points are actually symmetric. So I'll do that part quick then. So symmetric. Like that. And then coming down. So it would be like this. Like that. So if we were to now connect the dots, in the order that of increasing time, then it would look like this. Okay, and then the direction of drawing, if you can imagine, you know, like if you had a machine that was drawing this for you, it'd be drawing it this way. Okay, interesting. Any question about this? So now, before we started this exercise, I wrote that. And I want you to see that this is somehow related to this. These are somehow related, because here's the deal. So some things that you're expected to know before you get to this class is the conic sections. So you remember that from high school, all the conic sections? So in particular, I'd like for you to recall. So we've got, of course, this one, x squared plus y squared is r squared. Of course, that's the circle of radius r centered at the origin. That's what that one is. If we say, I want it to be centered somewhere else, I want it to be centered at hk, okay, then what you do is you replace the x's with x minus h's, and you replace the y's with y minus k's. And then that is the equation of the circle of radius r, but centered at hk. Now, if you take a circle and you symmetrically smear it out or squish it, you know, then it's not a circle anymore. What is it? An ellipse, right? So then, if you want an ellipse centered at the origin, then here's the equation for it. So x squared over a squared plus y squared over b squared, and then this is equal to 1. So now, if you were to take this equation right there, and divide both sides by r squared, then it would look just like this one, because the right-hand side would be 1, except now we'd have r squareds in the denominator, right? That's how it would look. And what I want you to see from this is that there's two possibilities. Well, we're going to take, just like the radius is positive, we're going to take that A and B are positive. So they're both positive. Now, one possibility is that A could be less than B. The other possibility is that A could be more than B, since they're both positive. So if A is less than B, what A says is that sort of, if this were a circle, then in the x direction it would have radius A. So it would look like this. But in the y direction it would have radius B, and because B is the big one, it would look like this. Okay. So this is an ellipse whose major direction, major axis, is aligned with y, and whose minor axis is aligned with x. So now, if A is the greater, then what's the distinction? It's like this one, but instead the y things are closer and the x things are further apart. So, do you observe that what we drew on the previous page is exactly this thing that I'm drawing now, except we only drew 3/4 of it. We only went from here to there. We didn't draw all the way around. Now, why didn't we draw all the way around? This will be the last thing we say before we quit. So why is it that this didn't draw all the way around? What would we need to go all the way around? Yeah, we'd have to change this to be a full measure of angle, right? Or, if you like, if we just wanted the top half, 0 to pi. Or if we just wanted the left half, pi over 2 to 3 pi over 2. Oh, that tells us how to draw just the part that we want. All right, so we'll continue talking about that next time. Have a nice Monday.